Good evening to everyone present here. Myself, Rahul Daya, and I warmly welcome you all to day 3 or our AICT ATAL Faculty Development Program on Next Generation Communication for 6G and beyond. We have successfully completed 2 enriching days with insightful sessions from experts in optical communication, computer network, and terahertz technology. Today, we continue our learning journey with 2 more remarkable sessions. A warm welcome to our faculty members, research scholars, and participants from various institutions. Thank you for your active participations. As we begin day 3, it is my privilege to introduce our speaker for day 3, session 1, Professor G. Thawasi Raja from NIT Trichy. He received the BE degree in Electronics and Communication Engineering from Madurai Kamraj University, Tamil Nadu, India in 2002, and the ME degree in Communication Systems from Tyagaraja College of Engineering, Madurai, affiliated to Anna University, Chennai, India in 2004. He received PhD in the Department of Electronics and Electrical Communication Engineering from IIT Kharagpur, India, under QIP, sponsored by All India Council for Technical Education, that is AICTE, New Delhi, India, in 2016. In June 2006, he joined as an assistant professor in the Department of Electronics and Communication Engineering at NIT Trichy, India. He promoted as an associate professor in the Department of EC at NIT Tiruchirappalli in September 2022. He was a lecturer in SSN College of Engineering, Chennai from September 2004 to 2006. His interest includes communication system, optical fibers, photonic crystal fibers, fiber optic sensors, fiber optic devices, optical waveguides, and reconfigurable and reprogrammable photonics, integrated circuits, and devices. He is a senior member of the IEEE in Communications and Photonics Society, member in Optical Society of India and Optical Society of America, that is OSA. Professor Thawasi will be speaking on the topic special fibers for next generation optical communication, a very important area that form the backbone of high-speed optical communication system used in 6G and beyond. Sir, am I audible? Sir,
Yes, sir. Can
I
you proceed, sir?
again request to Professor Thawasi Raja to take over the session.
So first
Okay,
of all,
sir.
thank the participants for giving me this opportunity to present some ideas on special fibers for next generation optical communications. This is partially related to my research area. So my main research area is related to uh, some of the photonic devices for communications and sensing applications. Initially, I started my research in the area of large mode area optical fiber for industrial lasing applications. And after that, I done some work with the help of my scholars in the area of crystal fibers, photonic crystal fiber based biosensors. Followed by I done some recently I've done some work in photonic crystal based waveguide devices for mainly for communication applications. Luckily, we have done some fabrications also with the input from IIT Dhanbad. Professor has given some input. Based on his input, we have done some collaborative research work and fabricated some devices with the help of Canada team. So that was one of our achievements we have done in this last 5 years. So now I will proceed to this allotted topic. If time permits, I will share my research team work also. So today's topic is special fibers for next generation optical communications. In the current scenario, we can discuss about many different specialty fibers for communication application, especially in the area of 6G communications networks. So I will start with this outline. So first we'll start with introduction to 6G and motivations and the role of optical fibers in 6G communications. So how the fibers are useful for this type of 6G communications and advanced next generation communications also. So coming to the introduction to 6G communications, I think many speakers also spoke about this. So as a basic introduction, 6G communications may be coming onto picture in the area of the era of 2030. Uh, in 6G communications, if you want to achieve high-speed transmissions in the order of terabits per second, then we need fiber as a main backbone with terahertz communications. So that will be suitable for AI-based unified networks also. So these three combinations, fiber, terahertz, wireless, and AI combination will be coming into picture if you are moving towards 6G and advanced communications. So it can be useful for ultra performance across different communication platform and as well as for sensing and computing applications also. So key technical targets, if you are moving towards 6G communications, the data rate should be in the order of terabits. This peak data rate I have mentioned. Mostly in the average data rate will be in the order of greater than 1 Gbps. The latency will be very small. Then reliability also we are expecting in high level, that is close to 100 percentage. The energy efficiency will be better than the 5G systems, 10 times of the 5G systems. The device complexity also will increase if you are going for high computational platform. You have to use the spectrum allotted also efficiently than compared to 5G system. So if you discuss about 6G frequency bands, so these are the different bands currently used for 6G communication applications. Sub-gigahertz mainly for long range coverage, FR3 towards 6G NR mid-band communication applications. Millimeter wave is coming close to 24 to 100 gigahertz, mainly for high-speed mobile applications. Moving towards terahertz band, that is from 0.1 to 1 terahertz or 10 terahertz. Mainly it's useful for chip-to-chip communications or backhaul and sensing applications. So this will offer, mainly we are focusing on terahertz if you are moving towards 6G applications. The reason is that massive bandwidths are available. It supports high data rate transmissions. Even we can go for terahertz imaging, sensing, other possibilities also available if you are moving towards this band. So as already pointed out, 6G will integrate most of the communication platform. So that's why people are moving towards 6G applications. For this type of communications, optical fibers play a crucial role as a backbone networks. So coming to the optical fiber in 6G communications, as already pointed out, if you want to achieve high data rate transmissions, the fiber is the only option. So this most reliable option also I can say, because it supports very high speed and low latency. So this will be immune to the atmospheric losses also. It's then compared to other systems, we can achieve high speed transmissions as a backhaul. If you're providing this backbone network for 6G communications, we can bring everything to our home. That we call it as a FTTX. We can integrate edge computing also with the help of this provisions. So I am just giving the summary of some of the recently reported literatures related to this fiber topics covering the 6G communications. So recently I have seen this literature, this reported experimental investigation of all optical sub-terahertz wavelength conversions for 6G communication applications. Why 6G needs advanced fibers. So these repetitive statements we can achieve high data rate as well as low loss transmission in the backhaul network. So mobile data growth also we can achieve towards terabits per second. So if you are combining this optical fiber and terahertz band, this is very essential for 6G platform that is covering high data rate as well as low loss and this low latency applications. So in this paper, what they have done is they have combined the terahertz option, terahertz hybrid link for gigahertz transmissions. This is the model they have considered. Mainly they have considered a single mode fiber. So other options also possible like photonic crystal fibers, multi-core fibers, free mode fibers also possible in the replacement of SMF. What they have considered, this is the network architecture they have considered. Then these are the available platform networks available in the communication platform. So this in a backhaul all are connected through optical fiber. This connection indicates these services are connected through SMF through the optical backbone network. So mainly they integrated this SMF connection between those services with the backhaul network. This is the model they have considered. Terahertz signal is carried over this fiber using optical single sideband modulation schemes. So they are considering some special options also possible for reducing the dispersion effect, but mainly they have used SMF fiber. So this is the model they have considered. This is our the conventional laser source. This is a gigahertz signal. So with the help of this optical architectures, they can able to transmit this gigahertz signal in this terahertz platform. This is the platform we can convert this gigahertz signal into terahertz by using this optical integrated base modulators. So this we call it as a Maxenter interferometer model. So with the help of this, we can modulate and transmit this gigahertz signal through this uh, optical platform using this optical platform. So this is one of the conversion methodologies. Using this, we can transmit our gigahertz signal over 6G fiber communication system model. So this one advantage is this enables fiber-based terahertz routing without any electronic-based controlling mechanisms. So in this setup, what they have proved is, so we can able to convert this gigahertz signal into terahertz signal using optical methodologies. So they have used the QPSK and QA modulation scheme for achieving this 4 to 5 Gbps modulation techniques. The fiber link what they have considered is 15 km SMF model they have considered this one. So coming to the special fibers related to this topic, so we can able to demonstrate, this other has demonstrated this terahertz over fiber transports using SMF, but we have the option for other specialty fibers like ICF and PCF also. So if you are using, they have considered only SMF options, but if you are using the specialty fibers like hollow core fibers or photonic crystal fibers, we can bring dispersion compensation mechanisms also. In addition to this, we can have some photonic processing. This photonic processing can be useful for easily integrating this gigahertz platform, gigahertz signal with the terahertz platform. So this is one of the advantage of going for this type of setup. So considering this scenario, now we can able to understand that in the backbone network mainly using the special fibers where the different options are available. Though people are preferring single mode fibers, if you are going for some special applications like conversions, some passive devices, those things and all, we can go for specialty fibers. With the help of that, we can realize the sophisticated communication system models. Now we'll see some of the specialty fibers currently in use for communication applications. So this structure shows the conventional optical fiber. So we all know that these are conventional optical fiber structures. It is having core cladding arrangements surrounded by the cable jacket for safety arrangements. This is a conventional one. Using this, we can able to transmit uh, our optical signal mainly for communication and other applications also. So this is one of the very popular structures. So as a modification of this, if you are going for high data rate and uh, have a sophisticated communication system, if you are integrating multi-user environment in this fiber environment, we can go for integrating multiple similar fibers in a single platform itself. So now we can see this one, this we call as a multi-core fiber. Each core will act like here we can see 7 cores are there. Each one will act like a one independent fiber platform, fiber independent SMF fiber model. So using this we can uh, achieve multi-user transmissions, something like space division multiplexing. So this will, each fibers are independently transmitting their information and to and fro, so that it will act like a space division multiplexing environment. So this is one of the very interesting modification from the conventional SMF structures. This is also already reported 2 decades before, but only problem is we have to maintain this less interference effect from the neighboring fibers. So we have to maintain some less interference from the neighboring fibers. This we have to maintain. So multi-core fibers, mainly it is suitable for 6G applications because it supports the same like single mode fiber. We can achieve this transmission in this SCL band. So we can achieve more than 400 gigabits per second. So this STM platform also we can realize using this type of multi-core fiber arrangements. So this will be useful for mainly for submarine communications also, as well as for data center and metro networks, because we have space division multiplexing arrangements, so we can transmit more number of users using multi-core fiber structures. There are a variety of modifications are already reported by the communities. So we have different options also available. We can have uncoupled MCF, coupled MCF, heterogeneous MCF. From the basic model, we can have the variations. So that is also possible. So that is mentioned here. Now we can see this one. This is a single mode one. Then we can have few mode fibers. Modification of this one we call as a few mode fibers. Slightly larger core. So larger core, you know the basic principles. If you go for larger core structures, multi-mode transmission will come into picture. We have to model this refractive index profile and the fiber parameters so that we can achieve few mode transmissions. Other than that, we can have single mode multi-core. Just now we discussed about multi-core options. Here also we can have few mode multi-core fibers. We can modify this structure so that we can achieve multi-core along with few mode transmission. That is also possible. These are the different options people are explored for communication applications. So mainly application is we can transmit high data rate as well as mode division multiplexing. Another combination is coming into picture. We can use the modes as a multiplexing mechanisms. Using this, we can able to transmit our informations. This will scale up our 6G longer communications. So multiple facial signals can be possible, channels and facial channels can be possible for improving our capacity of the transmission mechanism. Sir, am I audible, sir? Rahul, sir, my voice is clear or can I?
Yes, sir, it's clear, sir.
Okay, thank you. Audience, if you have any questions, please raise your doubts also. In between, I can able to clarify. So specifically, few mode fibers, as already pointed out, if you are going for few mode fibers, if you have multiple modes, this quality of the transmission is getting affected, dispersion, those things will come into picture. Same like single mode fibers. Even if you have multi-mode fibers, the conventional disadvantages, the multi-mode transmissions will bring intermodal dispersion, it will limit our data rates. These are the known phenomena. So if you are limiting the few modes, then the fiber structures, we can able to improve the data transmission. So that is the main idea of going for few mode options. We have many few mode options are already reported in the structure. So that is I have mentioned here. Step index also we have this few mode options, graded index, ring core few mode fibers, microstructures fibers also we'll see the detail in the coming slides. What is the meaning of microstructures? So these are the different combination of few mode fibers. Using this, we can able to control this delays during the transmissions. We can improve the capacity of the data transmission. All these things can be possible by different combination of fiber structures. Same conventions, people will use generally SMF and this multi-core fibers for communications. In alternate to this, people have reported the Philipp Russell group from Germany. They have reported PCF fiber also, mainly towards sensing and other special applications. So this slightly the structure is modified. It is they have derived the similarity from the SMF fiber, but they slightly changed the core. I mean the cladding core is fixed. The cladding is introduced with the help of air cool arrangements. If you are arranging the air cool surrounding the air cladding surrounding the core, in a hexagonal format. This forms the photonic crystal fiber. Basically, the core is surrounded by air gold rods in a hexagonal format. We call it as a photonic crystal fibers. The microscopic air holes running entire fiber length. So this forms the cladding. We have two options are available for core. That may be a air core. I mean the holes can be act like a core, or sometimes solid cores also possible. But generally the core is surrounded by the air cladding or low index rods that we call it as of crystal fibers, photonic crystal fibers. These fibers have some advantages. By tuning this air gold rod diameter and spacing between this air gold rods, we call it as a pitch period. By tuning these two parameters, we can realize many devices like dispersion controlling, or we can control the polarization effect. Many passive devices they have realized using this crystal fibers, mainly for communication and other sensing application, as well as for industrial applications also. This was already reported around 1996. After that, many structures has been proposed in the topic of photonic crystal fibers. These fibers will be useful for mainly towards sensing. We can realize nonlinear devices. We can able to transmit the power signal over the fiber. So many options can be explored using this type of fibers. So as I already pointed out, these PCFs are mainly suitable for next generation communications, because we have more flexibility in the designing the fiber structures that will be useful for realizing many interesting functionalities. This PCF structure, sometimes we call it as uh, single mode, we call it as effectively single mode operations. It will support the single mode operation over the band of wavelength. So that is a broad band, range of wavelength will support single mode operations. We call it as effectively single mode operations. That type of functionalities we can able to realize in the case of PCF structures. We can able to control the nonlinear effects. Low latency also we can able to achieve by tuning this fiber structural parameters. Mainly this cladding rods diameters and spacing between these rods is one of the two parameters. By tuning these two parameters, we can realize many interesting functionalities. From the PCF, we will get many modifications. So we call it as color core, anti-resonant color core fibers, solid core fibers, multi-core mode PCFs. Many combination of PCFs are possible, mainly towards terahertz communications, because this terahertz communication is mainly suitable for 6G applications. So terahertz range that is supported by this type of fiber structure is from 0.1 to 10 terahertz. So ultra high bandwidth will be available. That can be useful for transmitting our high data rate through this type of fiber structures. So this is a one type of modified PCF structures. We call it as terahertz PCF architecture. They have used, I think, topaz material. This topaz material based PCF design. So this type of designs are suitable for terahertz frequencies. This material especially they have considered. Generally people will use silicon material. Here mainly focusing on terahertz, so they have used special material like topaz. Using this, they have realized a rectangular air cap core. So this core is something looks like a rectangular core. Now that is a zoomed version is given here. This structure is created using air cap. So this entire structure is created using the air cap with 36 square slots. So within this one, you can see 36 square slots are there. This air cap core with 36 square slots are used for realizing the rectangular air cap core structures. Cladding is made up of multi-lattice circular air holes. So as already pointed out, these structures will have air claddings. So by tuning this rod diameters and spacing within these rods, we can able to tune this operating wavelength mainly towards terahertz applications. So this type of structures generally achieves low loss, strong mode confinement and high power confinement in the core region, especially for better confinement of our signal for long distance transmissions. This picture shows uh, there's an electric field distribution plot for X and Y polarizations. So these two types of polarizations are supported here. This core shape supports strong intensity localization. So mostly the confinement effect in this core is more, so that the light is well confined in the core structures. This will be suitable for long distance communications also. Just some of the data I have taken from this literature. So this will be mainly suitable for 1.5 to 3 terahertz. Y polarization modes will have high effective index, so that this Y polarization component will be having better confinement. Using this, we are able to transmit our signal, then we can achieve long distance transmissions. It will be useful for stable single mode terahertz communication applications. In addition to that, this type of fiber supports Y polarization, especially it is having high fiber impingance, so it will improve the polarization stability also. Further, it reduces the dispersion component that is arises due to this polarization, because it supports high effective index for Y polarization. The polarization mode component will be less compared to the other fiber structures. So this information I have taken from this graphs given in this paper. It recently reported in IEEE conference. So this coming to this some more details. This Y polarization, you can see the difference. Better confinement is there. It's almost compared to X polarization. 46% of light is well confined in the core region for Y polarization components. So the same information is given in a different vectorial plot. So I will skip this one. As a modification of the previous structures, we have other options also. First, we have started with PCF. Then we have this topaz based arrangements, topaz based this structure. Now we have this Kalo core fiber structure. This is also another version of PCF arrangements. The core is Kalo core. This surrounded by the air holes. This white color circles indicate air holes. These structures nowadays very useful for communication as well as sensing applications. This fibers guides the light in the air, not in the silica. So this air core is nothing but a hollow core. The light is well confined in this air core through photonic band gap, or we can use anti-resonant mechanism. So you'll see this anti-resonant fibers in the coming slides. Mostly this type of structures will use photonic band gap technique for confining the light in the air core regions. These fibers will have low latencies, and nonlinear effect also comparatively low if you are comparing with solid core fibers. These high shear fibers are emerging as one of the important technology for ultra fast low loss communication applications. So some of the details related to this one. So this also supports SCL band transmissions. And then you can have this mid-air transmissions also supported in this range. We can achieve the data rate about 100 Gbps, a single line over 100 meters. Major advantages: this 30 to 40% low latency versus glass fibers. So conventional fibers, if you are comparing, it's better advantages available with these fibers for 6G communication applications. So another fiber also I'm considering here, that is we call it as anti-resonant fiber. Same structure, similar structure. So here also we are using air core, but another modified version is resonant fiber, anti-resonant fiber structures. Now we can see here many rings are available surrounding the dark space indicate, dark black color indicates it's nothing but a air region. This white color indicates silica region. So now this, what is the idea of this type of structure is this surrounding rings will act like a anti-resonant mechanism, something it's act like a mirrors. It will confine the light in the core region, air core region. So now we can see here some of the important parameters they have mentioned. D1, this is the diameter of this rod. This is D. Then this is the width of this ring. Small ring is W. Just I'm pointing the arrow here. This width of this ring is W. This is the gap between these two rings are D. This diameter is D2. This is D1 and D2. So using this different parameters available, we can tune these parameters while doing the simulation study. we can able to achieve better confinement in this core region. This type of fibers very recently reported by NTU group also. Many this fiber structure is reported very recent days, and I mean within this last 10 years durations. This type of fibers are mainly useful for sensing as well as for communication applications. So these structures mainly they reported with this parameters. So they have proposed these fiber structures for communication applications. The main idea is something this surrounding rings will be acting like a surrounding rods will be acting like a anti-resonant mirrors. It will confine the light in the center region. So this type of arrangements we call it as anti-resonant fibers. These anti-resonant fibers have six circular anti-resonant tubes to lack it's useful for confining the better confinement of the light in the center regions. By using a different arrangement of these rods, we can realize polarization effect also into these fiber structures. So we can control the polarization components by properly introducing the assimilar rods. You can see here four rods are similar, two rods are having different structure. This horizontal rods and vertical rods will have different structural arrangements. This horizontal two rods are having smaller in size. I mean they are in smaller in size. That will be useful for realizing the polarization effect. By controlling this polarization components, we can realize uh, single polarization and single mode transmissions also possible. So here also you can note down this almost 50% of the efficiency is well confined in the core. So this type of fibers are mainly suitable for terahertz communications. If you are using materials like topaz, this will have low absorption, material absorption in the terahertz band. So this type of topaz based ARF fibers will be suitable for terahertz communications. Moving further, so roll up terahertz fibers, these are all some known parameters. We can achieve high speed, I mean high data rate transmissions in this band. This will be suitable for 6G applications, mainly like XR, VR and holographic communications. This will support low loss in the terahertz fiber, especially for networking applications. So this mainly designed for terahertz communications. So this will support further fire engines, also high fire engines. So we can able to realize polarization effect for communication applications. So that is the idea of this one. So same data is reported through different graphical representations. So this was reported by Rahman Group et al. In ICTP 2023. So this type of fibers will act like one of the strong candidate for 6G next generation networks. This was very recently reported in high quality journals also. I have seen similar fiber structures with different modifications. They are mainly reporting for communication and networking applications. So further modifications also possible because our focus is towards 6G communications. So in that range, we are only the terahertz band is more suitable for realizing optical fiber-based communications. So in terahertz band, other type of fiber structures also available. So that is reported here. Coming to this fiber classifications, we have different options. So this photonic crystal cladding, anti-resonant guiding, porous core structure, slotted core, all these types of structures are available. So the fiber structure is given here. The first one we call it as solid rod fiber. The second one is microstructure fiber. The first one is a conventional fiber structure. The modification from the conventional, we are getting this type of structures. We call it microstructure. This one we call it as a porous fiber. This one we call it as a suspended fiber. So many combinations are available. Nowadays, people are using this type of fibers for sensing applications and industrial applications also. But this type of fibers, if you are using special material that is suitable for low absorption and terahertz band, then we can realize terahertz communication using this type of fiber with low loss and high data rate. So some of the fibers is reported. This structures I have taken from this literature, the optical express reported by MS Islam Group. Mainly coming to the guiding mechanisms, as already know for us, in the conventional fibers, we are using total internal reflection phenomena. If you modify the structural parameters, you will get modified total internal reflection phenomena. Though this one we call it as modified. The reason is that here the core is not well defined because the core and claddings are realized using this type of arrangements. So now this type of arrangements, there is a chance for leakage effect also. If you are not properly modeling this air hole rods in the cladding, it will leads to leakage effect. So this type of this guiding mechanism we call it as modified DAR effect. This one we have already seen that this is hollow core fibers. Mainly the light is confined in the low index region. We call this a botanic band cap effect. Coming to the another category, that is anti-resonance guiding. This already explained. So it's something, this act like this cladding rods and this arrangement, structural arrangements acting like mirror arrangements for guiding the light in the middle region. We call it as anti-resonance effect. Some of the fibers we call it as resonant fibers also available. Using the resonance mechanisms, we can able to couple the higher order modes into the resonant fibers. Those fibers also reported, I have not mentioned here. So this is something like anti-resonant fibers. So using this one, we can realize mirror effect for confinement of the light in the core regions. The third one is gummy fibers. These fibers are using incubated coupling by properly, this one is gummy fiber. Sorry, this is we call it as anti-resonant fiber. This is the incubated coupling. This structure is they have this core and cladding arrangements. You can see here. We have this special fiber structures. These arrangements we call it as gummy arrangements. Using this, we can realize the coupling effect in this core regions. So practically realizing this type of structure is a little hard compared to this other mechanisms, but this is having some special effect. We can realize this one for communication as well as for sensing applications also. So we have seen different fiber structures now. So using this different structures, we can use appropriate material. We can guide the light in the effectively in the core region. So material is currently available, that is Xeonax, Topaz and Teflon, and HTP, high density polyethylene. These are polymer materials also available. Using these materials, we can realize terahertz fibers for communication applications. So coming to the fabrications, so audience, if you have any doubts, you can ask me the question because we are a little faster. Audience, if you have any doubts, till now, if you have any doubts, we can have some interactions. No comments from audience. Do you have any doubt?
There is no comment, sir, from the audience.
Okay, thank you. So this is slide shows the overall fabrication possibilities available for terahertz fibers or specialty fibers. We can have drilling mechanisms. You can have the fiber structures. That is, we call this a preform. In the preform, we can have drillings. Using these drillings, we can realize different arrangements of the rods in the cladding as well as core. So another option is feasible option is stack and draw. This is one of the very popular methods. First, we will prepare the different rods with the different dimensions. Then we will stack it, and finally we will go for fiber drawing, that we call as a stack and draw methods. And we have other options like sacrificial polymer and extrusion techniques also possible. Depends upon the fiber complexities, we can go for this type of options also. So recently people are going for 3D printing also. So using this, we can realize this type of complex fiber structures. Mostly people are nowadays using stack and draw, and commercially people are not going for 3D printing. So these are the options are available for realizing special fibers. Applications already pointed out. So terahertz communications, we can use this type of fiber structures. You can go for sensing as well as for other applications also. We can use this terahertz fibers. So other options available. So these are the things I have taken from this literatures. So coming to the plastic fibers, this is another variety of optical fibers available. So this type of fiber structures are mainly useful for industrial and other application. I mean, mainly for uh, short distance communication, because the loss is severe. So this type of fibers are not proposed for communication applications, mainly for short distance and some of the decorative applications, like we can use this one for using this visible lights. We can use this one for sensing applications as well as for automobile applications. We can short distance automobile applications, automobiles also we can use this one. This fibers mainly useful for biomedical and other communications also. Here also we have different options, but mainly this type of fibers are suitable for uh, automobile and other biomedical applications. So here also we have many varieties are available. So different types of plastic optical fibers are available. So that is reported here. So from this one we get an idea that we can use this type of fibers mainly towards um, submarine communications or cloud computing, and we can use these fibers for mainly towards uh, reduction of low energy consumptions. We can effectively use this one less power consumptions, and we can, with the help of this, we can achieve sustainable infrastructure uh, environment, so that we can save the environment also. So different configurations we can use for different types of applications. So other special fibers that is available is the polarization maintaining fibers, algozinide fibers. So it depends upon the requirements. We can use different fiber combinations. This one already pointed out, polarization maintaining fibers. In the given fiber structure itself, we can realize this any one of the polarization components by modifying the structures. That will be useful for well confinement of any one polarization in the core region, so that we can achieve high confinement, that is for long distance transmissions. Coming to the algozinide fibers, this is coming under the nonlinear fiber categories. Using this we can realize tunable mechanisms also. Using this fiber we can realize tunable sources. Other possibilities are available because this is coming under nonlinear fiber category. By realizing this nonlinear effects, integrating this nonlinear effect in this type of fibers, we can use this fiber for realizing some interesting applications like tunable sources and sensors. Many things we can realize using this one. This another variety is we can use fiber arrangements for realizing this orbital angular momentum for efficient communications. So this one type of fiber communication methodology is useful for transmitting our signal more effectively. This is a teleradio fiber. Based on this material, we have another combinations. Dispersion shifted platen fibers are very conventional one. We can realize this type of options in different fibers using these structural tuning. Other options like photonic band gap fibers. This is also very useful for realizing um, terahertz communication, especially for 6G and other applications. So these are the references I have taken. From these are the contents I have taken from the references. Special fibers mainly towards uh, overcome the limitations that is reported in the traditional single mode fibers. This will support terahertz data transmission and ultra low latency and efficient 6G communications. So many advanced technologies like STM, special division multiplexing using multiple cores, mode division multiplexing, that is also useful to realize using the fibers like few mode fibers. then coherent communications and mid-layer transmission. All these advanced technologies we can realize using this different fiber structures. So for this one, we can use fibers like PCF, photonic crystal fibers, and other hollow core fibers, then multi-core fibers, P-mode fibers. This exception is for plastic optical fiber. This is not that much suitable for long distance communication because of the high loss. And other special fibers also reported in the literatures that will be useful for optical backbone networks. So mainly this is suitable for fast, reliable, and intelligent 6G communication applications. So these are the literatures I have taken for this preparations. Participants, if you have any queries, you can ask me the question.
Thank you, sir, for giving the detailed knowledge about the different type of fibers, especially mode fibers with different structures, and why PCB is important for the next generation communication, and also for the hollow core fiber with different arrangements, and also why terahertz optical fiber are important for 6G and 7G. Thank you so much, sir, for giving the these type of details. Online participants, those who have the queries, any queries, they can type in the chat box.
We can have a discussion for another 10 to 15 minutes. We can have.
Sir, can you share your email ID in the chat box so that they can connect directly with you, sir?
Yes, I will do that. So participants, if you have any queries, you can share your doubts also through my mail.
There is one question, sir, from the participants, sir. How will leakage losses affect in multimode fiber during communication?
So what is the question, sir?
How will leakage losses affect in multimode fiber during communication?
So multimode fibers, so we are aware about in multimode fibers we will have large core. If you in the case of you are considering multimode means automatically the fiber core structure is slightly larger than the conventional fiber structures. Because of this slight variation in the core size, we are experiences multiple multimode propagations. If you are going for multimode propagations, it's same like multimode fibers that is available in SMF structure also. If you have multimode, then automatically the light energy will be spread across different modes. Then it will affect our communication property or confinement property because of this intermodal dispersions. When multiple modes are available, that will create intermodal dispersion effect. Generally, people will have different options for controlling this. We have graded index options, or we can properly tune the refractive index profile. We can modify the structural parameters. Using this, we can able to control this leakage loss because the confinement property is getting affected when if you are going for slight variation in the core structures. I think I answered the query, I guess.
Yes, sir. Yes, sir. Thank you, sir.
Yes.
And the second question from the audience is, what are the challenges in implementing PCF? in 6G networks?
Challenges we have to, because main application is we have to go for mainly towards we can see that low loss transmission we have to achieve perfectly. We have to realize some, if depends upon the requirements, we can realize the different fiber structures. Mainly if you are focusing on communication applications, the terahertz fibers is one of the best options. We can realize PCF structures towards terahertz band. So we can with the different material combinations are available. Using this different material combinations, realize your fiber structures that will achieve low loss, high data rate transmission with better confinement. So we can focus on low loss as well as for, because materials will absorb the light that is propagating through the structures. You have to use appropriate material that is useful for realizing low absorption as well as for low loss. Then if you are planning for this better polarization confinement, polarization effect also in the realization, then design a structure accordingly so that other dispersions also we can able to control it. Focus your band,
Yes, thank you.
focus your
Yes.
applications, then accordingly we can tune the fiber structures for specific applications. Not only for communications, we can go for other application like sensing and other industrial applications also.
Yes, sir.
Decide your application.
Biosensors and those things.
Yes, thank you, sir. Thank you.
Thank you so much, sir, for your detailed and insightful session, sir.
Thank you, sir. Thank you very much.
Thank you, sir. On the behalf of the all participants, myself, Rahul Daya, expressing our heartfelt gratitude, sir.
Thank you, Dr. Rahul. Thank you very much for your support. Thank you.
Thank you, sir.
Thank you.
We will now take a short break. Yes. Sorry, sir. We will now take a short break. Please rejoin us at 7:30 p.m. for the next session.